As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kind of like the strengths of those connections, and the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer, that output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is, and how bad the computer should feel. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow. So instead, you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples.